Hi everyone, good afternoon. First of all, thank you ACI for the invitation. So I will do my best to show you a little bit of what innovation is, why it's important to understand the value chain in order to push innovation. I feel that my presentation will echo a lot of the comments that have been done in the last two presentations, including the international launch. I'll show some case studies and then I will conclude with some remarks. When we talk about innovation, we think about bringing something new, right? Developing a new device, and we think about iPhones. iPhones did a great accomplishment, launching something new. Everybody waits for the next generation iPhone, and everybody's buying them, right? People adapt quickly in terms of the technology in this area. If we take a look to what computers, since the computer first was developed through now, it's impressive what happened, right? Nowadays, we communicate with social media. We all of our are connected with not only with Facebook or Instagram. We even do a lot of business through LinkedIn. That's the way nowadays we actually do a lot of marketing, right? So this industry have developed and has adapted quickly. We talk about innovations after the innovation. What you see on the left side of this slide is innovation out of the innovation. After the iPhone and the new smartphone were developed, new innovations were created. Now we see those pockets to put the cards or to put the money. We have these little block devices where you can do commercial business immediately, and then nothing related with iPhones, but you have on the sustainable side, you have reusable bags that were developed to meet the need of changing from a plastic bag to something that is more sustainable. Getting back a little bit into the devices, now we have even myself, I do have a smart pen that we use to write and become more sustainable instead of using a lot of papers. We use these electronic devices. However, in construction, the adaptation or acceptance of innovation is not as quickly as we see in other areas. I'm showing here the trajectory of the admixtures. In 1960, we saw the first super plasticizer that was developed. And then in the 80s, we saw the polycarboxylate coming to revolutionize the admixture area. We saw those used in Japan, as you see in the example over there. And then later in the 90s as well, we saw the first self-consolidation concretes being developed. So it takes a long time. Our industry takes a lot of time to accept the new products, new innovations, something new. But there's a reason behind, right? There's some limitations. We need to recognize that there has been some catastrophic situation that put us to think, right? Or to be apprehensive of accepting something that is new. And the reason why is because if something is new, then there's no reference. People and engineers our industry looks for references. Nobody wants to be the guinea pig. Nobody wants to be the first one to try. But at the same time, if you're not the first person to try, then there's no history, right? So it's like the chicken and the egg kind of a story. But that's how it is. And we have to continue to work on this situation and moving the industry to a more innovative industry. So what I'm showing here is a very structured stage gate process that is followed for every company. Every multinational company has their own stage process to develop a product or develop a solution. I'm using the McKinsey one, so it's well recognized everywhere. And what I wanted to show here is not the specific process, it's the fact that it's very structured and that behind this process, every company, every supplier company like us, address the fact of the return of investment. If we invest money, in a project to bring a solution into the market, every supplier wants to see the return of investment, and that's a reality. So those are challenges that we face, because then we need to push internally in our organizations to address certain issues that we see in the industry. So in summary, the industry needs proven technology in order to move forward with something new, right? At the same time, these big organizations, such as the one that I'm working with, also need the value proposition well defined, needs to make sure that the return of investment is there, which brings also limitation as well. But what I'm going to show here is that the industry is moving into the different direction, and that we are looking to get out of this scenario. So what can we do to accelerate this? The intention of my presentation is to show some case studies where we have changed our mind, the way that we think, to address certain issues in some projects. And the way that we have done a successful work is looking at the whole value chain of the situation. When I talk about the whole value chain of the situation, I mean, what are we dealing with? Are we dealing with a new project? Or are we dealing with an existing project that faced a little issue, as you see here? Once we understand that, we also need to understand how the solution will be applied, right? That's important at the end of the day. And when we do that, we come back to the lab. We met with experts, and we analyzed the standards, and we decided what it needs to be done in order to get into that specific solution. Then you need to make sure that you can produce that new solution and that you can supply if it's something new. So this is an iterative process that we follow in different cases, and we have to do that if we want to address certain topics or certain issues that we face in the industry. And we have to have an open dialogue with the different stakeholders to understand how we can bring that new solutions into the market. This is my introduction to start talking about 3 specific projects that shows this whole value chain out of the box, out of the specs of following a strict protocol, and being more flexible to find solutions in 3 different situations that we have here. The first 2 are going to be related with projects in Latin America. First one is in Panama Canal. I'm going to talk about this gorgeous bridge, cable stay bridge, that was awarded in 2012 in Panama to an international contractor. This bridge was almost $400 million of investment. It's the 3rd bridge over the Panama Canal. They're working on the 4th one right now. And the issue here is that this project was awarded to an international company that did a tender, understanding that they will not face any situation at the local level. They face an issue with concrete. Workability was a big issue, and also the viscosity of concrete. These slides here show a little bit of the history of what happened. In 2012, as I mentioned, the bridge was awarded to this design and build company, and they start working on the project. And in Q4 2012, they start facing issues with the concrete. Guess what? They didn't knew that the local materials were not meeting the standards, specifically because this is a European company that didn't have any experience in Panama before. So they struggle to pump the concrete, they struggle to maintain the workability, and that's when they call us to be part of the equation and to find a solution to overcome these challenges. The solution was developed, and I'll talk a little bit more about the solution, and introduced into the project at the end of 2013. So they really struggle with this situation. So basically what happened is that everything started by the fact that the project required a high durability. And with that, the designer or the owner, which is the ACP, Autoridad de Canal de Panama, required that the RCP numbers or required for the bridge was all the concrete needs to meet below 1,000 coulombs. With that, low water receiver ratio is needed, and in addition to that, the materials available were manufactured sand, very harsh sand, and they have to use supplementary cementitious materials such as silica fume, natural pozzolan, and others. So when the project started, they did not take into consideration the viscosity of concrete. They were, they got the strength, they got the coulombs, they got what they needed, but guess what? They were having issues in the pumping of the concrete. And they brought together several stakeholders to discuss what we can do. We need to address this. We were one of them. And we come out with the fact that we have to take a look to the viscosity. We took T50 as a test of method for viscosity. Since we were in the project and in Panama, everybody has a rheometer available. So in practice, we use something that can be used in the project. And when the first reference design mix was measured, the viscosity in terms of time for T50 was 10 to 12 seconds. Among different stakeholders, the conclusion was that in order to mitigate this issue, we have to reduce the T50 to 7 seconds. So we worked on the mix design with the contractor, and we ultimately got a new solution that helped them to decrease that viscosity and solve the problem. The situation here is that, as I mentioned to you, when a design and build company, a multinational company, get access to this type of projects, they just follow what they used to follow in every generic big project. They go look at the specifications, they go to the tender, and then once they get awarded, they work on the project. But they didn't realize they will face such quite of issues with the concrete. So what was key on this project was the fact that we had, at that time, we had a very structured project in Germany where we were developing a new molecule, but it was not ready to be launched. Fortunately, the fact that we were working closely between US, Panama, and Europe, we decided, okay, we need to do something. We need to address this issue, and we carefully decided that we have to take a risk and launch and put this product into Panama to see if that will help with the viscosity of the concrete and all the other requirements needed for the concrete, and we succeed. It was a big push. We knew that we were not fully ready to do this, and there was a lot of logistics behind, but finally we were able to succeed. And with these slides, I will close this case study to move to the next one. And my message here is as follows. The key part to be successful in this particular project was that we look at the whole value chain. We look at what ACP or the owners want, the Autoridad de Canal. We look at what the contractor and engineers were facing, and we look also at the concrete, right? And we address every single part of the whole value chain before we decided to take that new technology out and decrease the viscosity of concrete and solve this big issue. Now I'm going to move to the second one. This is related to the underwater grouts, and I'm going to spend here more time than in the other one. So first of all, this is related about the rehabilitation of Ituango Dam. Ituango is the largest power station in Colombia, 225 meters tall embankment tank, And this project has 8 huge turbines to generate energy. The energy that this dam generates, or hydropower project, generates 17% of what Colombia needs in terms of energy. So imagine that. And the issue with this specific project, which you see a picture of it, is that they were into some delays that took them to the rainy season. And then I'm going to pause here. In Central America, as a background, in Central America, there's no 4 seasons like in the US or maybe in other part of the world. There's 2 seasons, the dry season and the rainy season. So in this particular one, the project delay make them into the rainy season. And with that, there wasn't the possibility of having the project completely compromised because now you have more water that you did not consider during the schedule of the project. So what happened here? We're in the rainy season. There was a high debris of water flow going through the main 3 diverting tunnels that were, as any dam, you have some diverting tunnels to take out the water from the Cauca River, to divert the water from the river. And due to the fact that we have this rainy season in the equation, one of the diverting tunnels was clogged with a lot of debris. If you look into the internet for this specific project, there was a lot of issues around the project, but we're going to focus just on this one. And what happened here is that the fact that they got these diverting tunnels clogged, they have the water causing a high pressure, and they have to basically wait for a few days to decide what they have to do. They tried to unclog the tunnel. It didn't work. So they had to put out 9,000 people because of the situation. It was a whole crisis because if they didn't solve this situation, they have more than 100,000 people will be affected for that. So basically what happened is that they were a lot of under pressure, so they have to divert the water through the house pump, unfinished house pump. So you can imagine how big was the loss of the turbines. That's a different story. That was millions lost. And the fact that this project was originally an investment of $4 billion projects that end up in additional cost. But they had to do it. They have to run the water through the pump house. They fixed that issue. They fixed the pressure of having the water flown and avoiding any catastrophe, further catastrophe in the country. But at the end, they have to do something with the diverting tunnel. These different designers, consultants met and decided that they had to close one of the tunnels that collapsed, and they would no longer use it. And this is a picture of how it looks, a pictogram of how it looks, obviously. And the solution that was basically designed or proposed was to create some pre-stopper in the tunnel and inject or generate some micropiles to inject underwater grout and also a resin material. You will think, why they don't do it with only resin? The issue is cost only. When you have a cementitious material, it's more cost effective than just filling everything with resin. These micropiles were injected, and this pictogram shows how the first pre-stopper was done, and at the end, the resin was introduced to fill out the remaining voids. Once the 2 pre-stoppers were done, they remove the excess material inside of the tunnel and they backfill it and they close it. They have to do it in order to stabilize the mountain because there was some issues with the stabilization as well. So what did we do here? We had to develop quickly a new solution that was not in the market, and we have to address this quickly. We need to have a underwater grout that was required to be pumpable for more than 130 feet. Needs to have an open time of more than 1 hour. Obviously, the requirements of strength are there clearly. For 20 days, for 56 days, they have 70 megapascal, as I showed before. And in terms of anti-washout properties, they knew that the tunnel already have water running. So the material must stand 340 liters per minute without losing more than 30% of the material. So how do you prove that? We have several collaborations with the designer and the different stakeholders, the contractors, and so forth. And in order to simulate what was happening there, 130 feet away, we have developed a fish tank as a mock-up. And we did that in our facilities in the US, but also we did it in Colombia. So we were basically doing the iteration that I mentioned at the beginning. We did it 3 times in order to get into the right solution to incorporate this grout into solving this issue. What you see there is the fish tank that has an inlet and an outlet. In the outlet, we have a drum that collected the water that was exiting, and by measuring the density of the water, we evaluate how much material was lost. Everything, it was not us only, it was a team of people. It was the designer involved, it was the contractor and several other consultants and ourselves trying to figure it out how to solve this situation. What you see in the middle is a picture of one of the prototypes that were conducted, and we basically saw that it looks good from the outside. It seems that actually the product was injected correctly, but at the same time, we took several cores to analyze the consolidation of this material. So for us, it was a lot of thinking behind. We had the knowledge of the grouting, we have the knowledge of underwater concrete, but we put together a set of experts to figure it out how to address this situation and how to address the fact that we have to have certain gradation in order to inject this grout. So we end up putting 1,200 metric tons of grout produced in the US and supplied to Colombia, and storage in very controlled temperatures containers in the middle of the jungle in Colombia at 90 plus degree of temperature, and we were able to succeed on this. So it was obviously a lot of stress and a lot of people involved in this creating this solution, but we were lucky. No, obviously, we had a lot of success on doing this. The last case that I wanted to show is something that is not in Latin America. It was done basically in the US, and it was done maybe 2 or 3 decades ago. But we thought that it was important to mention this as well. When refractories were something big, and shotcreting refractory concrete was something new, we didn't have the right solution available. And we find out there was some pumping challenges with this material, as it's a dilatant material, and we also knew that in order to do shotcrete, it must be non-sagging. So when we look at traditional solutions for shotcrete, we think about sodium silicate accelerators as a traditional accelerator, that doesn't work in this type of solution. And the reason why is because we're talking about refractory. So those materials have a very deleterious properties on this type of refractory concrete because it softens the properties of the material. And in addition to that, the typical superplasticizers were not able to overcome the dilatancy. So our team, I was not there, but I was part of the other two, but my colleague Rick First was part of this specific one as well. And he said that they met and they start thinking and drafting possible solution and they end up thinking about corn starch. And they said, well, we use corn starch to increase the viscosity of soups. Then you end up talking about food and all of that. And finally they said, okay, we need a thickener that will hold the concrete. And that's what they did. They, instead of including a traditional accelerator, what they did is they introduced a thickener in the nozzle, being able to make the concrete hold in the wall. And in order to overcome the dilatant properties of the concrete, instead of using a superplasticizer, they foamed the concrete. And in combination with the high compressed air, they were able to meet the requirements. And finally, when you look at refractory concrete, you always will find a thickener involved and an air entrainment involved. And this is the reasoning behind. This happened decades ago, as I mentioned, but we thought that it was critical to mention that. We have done this before, we continue to do it, and as an industry, we need to take into consideration that our industry is slow into adapting to new innovation, and sometimes we need to face huge issues or requirements in order to accelerate the process. But I have shown here that if we take a look at the whole value chain, at the whole scenario, and if we take a look and talk with all the stakeholders, and we assess the risk, we can definitely move forward with more innovation in our industry. So I invite you guys to continue to embrace innovation, and hopefully we can continue to move forward. Thank you so much.